we will have to go travel to Oklahoma, University of Oklahoma. There's 3 presentations from University of Oklahoma. The first one is about innovative multi-hazard resistant bridge columns for ABC. Dr. Jeffrey VOLZ from OU is going to present this. And Dr. VOLZ.
Okay, thank you, everybody. My presentation today is going to cover our project on innovative multi-hazard resistant bridge columns for accelerated bridge construction. Again, my name is Jeff VOLZ. I'm the PI on the project. My co-PI is Dr. Royce Floyd. And the 3 students working on the project are Jackson Milner, Omar Yadek, and Zach Thierry. I'll first go over some background and rationale for our study, and then our goals, objectives, and tasks, the work that we have completed since the last research day, and then happy to answer any questions that you might have. Numerous methods exist for accelerating bridge superstructure construction, but there are a few methods that exist to accelerate bridge substructure construction, and that's the focus of our research. We're investigating a novel bridge column that, in addition to increasing the speed of construction, also has enhanced ductility and energy absorption characteristics compared to traditional reinforced concrete columns. Our research is basically the next step in an evolution of alternatives to the traditional reinforced concrete columns. Some investigators started using steel tubes filled with concrete, where the steel tube would act as a stay-in-place form and eliminate the need for a reinforcing cage. These columns showed enhanced ductility compared to a standard reinforced concrete column. Unfortunately, placing the steel tube on the outside exposes it to corrosion, and you have to protect it as you would a steel beam in a bridge, but it is always more susceptible to corrosion and deterioration. To try and combat that problem, other researchers have examined fiber reinforced polymer tubes filled with concrete. The FRP tube is resistant to chlorides and other deleterious materials, but unfortunately, these columns did not have as good ductility because the FRP, of course, is a very linear elastic material up to failure as compared to steel, which has a nice plateau. Other researchers have examined hollow core concrete columns, the idea of making it able to reduce the weight of the columns and using them as precast elements shipped out to the job site. So the hollow core would eliminate a lot of the concrete in the center that didn't add to the strength and durability of the system and make it lighter for shipping it to the job and erecting it in place. There still had to be splices made, either reinforced concrete splices or potentially post-tensioning the segments together, but it was an additional benefit in terms of reducing the weight and increasing the speed of construction. Our research project aims to combine the best parts of all of these previous options into a novel column that provides enhanced ductility and resistance to multiple hazards, as well as speeding the time to construction. The concept involves an inner steel tube, an outer fiber reinforced polymer tube, and a central concrete core. The inner steel tube and the outer FRP tube act as stay-in-place forms, eliminating the need for formwork and the cost and time of erecting that formwork and then taking it down. The inner and outer tubes also provide confinement for the concrete core, increasing its apparent compressive strength. The steel tube on the inside provides the reinforcement and the ductility for the system, while the FRP tube on the outside enhances the durability because the FRP is resistant to chlorides and other deleterious materials and protects the concrete and the steel on the inside. The concrete core prevents local buckling of the steel tube and the FRP tube, improving their characteristics and behavior. In terms of the goals, objectives, and tasks for our study, our overarching goal is to implement these hollow core FRP concrete steel columns for accelerated bridge construction. And our objectives consist of determining the benefits of using either high-strength self-consolidating concrete or ultra-high performance concrete for the concrete core, and then developing design procedures and recommendations for the steel, concrete, and FRP wall thicknesses, concrete type, and nominal flexural and shear strengths of the HCFCS columns. We have 5 tasks to accomplish that goal. The first one is to design and construct our columns. Our columns are basically half scale. They are a nominal 18-inch diameter. The steel tube on the inside is a nominal 12-inch diameter. The FRP tube, a nominal 18-inch diameter, which leaves a 3-inch thick concrete core. We also design and construct a traditional 18-inch diameter reinforced concrete column that will serve as a control specimen for our test specimens. We'll test the columns in increasing cyclic load under a constant axial compressive load. The column specimens consist of a reinforced concrete base, the column section, and then a loading stub where we apply the constant axial compressive load and the cyclic loading until failure. We'll then perform a parametric finite element analysis so that we can extend the results of our test system, because we're limited into the number of specimens we can make, but doing a parametric study will help us get a better feeling for the behavior of the specimens and variations in the properties and thicknesses of all 3 materials. We'll then develop design procedures and recommendations for the design of these columns, and then disseminate the information through our quarterly reports, final report, this research day, other webinars or seminars, journal publications, and conference proceedings. Last time, at the previous research day, this is where we were at. We had constructed 4 of the concrete bases with the embedded steel tubes, and we're ready to advance to the next stage. So during that period, we added reinforcing strain gauges to the steel tube to measure longitudinal strain during testing. There are a series of 4 strain gauges, approximately 3 inches above the concrete base, and then another set approximately 9 inches above the concrete base. Once those strain gauges were installed, we were able to lower the FRP tubes into place, make sure that they were centered around the steel tubes, and then secure them in place with a halo at the top and the braces. This would allow us to place the concrete without disturbing or moving the FRP shell to complete the construction of the column. We fabricated 2 specimens with high strength self-consolidating concrete. This SCC mix reached a 28-day strength of 10,000 PSI. It flowed very easily into the 8-foot tall column from the top. It required no external or internal vibration to fully fill the annular space between the steel tube and the FRP tube. We also poured the ultra high performance concrete into 2 of the specimens as well. This material also flowed very well. It has a 28-day compressor strength nearing 20,000 PSI, and it's the non-proprietary UHPC mix that was developed and tested as part of some earlier ABC UTC research studies. Again, this flowed very well through the 8-foot tall column, causing no segregation and no voids, and did not require any internal or external vibration. That was one of the benefits of using both the self-consolidating concrete for some of the specimens or the ultra high performance concrete, because then we can place it without any vibration, which also speeds construction and cuts down on cost. We also installed strain gauges on the longitudinal steel for our traditional reinforced concrete column that serves as a control specimen. We located the strain gauges at the approximate same locations as those that were installed on the inner steel tubes for our novel column design. And then we cast the concrete for that column so that it's ready to be placed in the test setup. The concrete for this column had a 28-day compressive strength of 6,000 PSI to match a typical Oklahoma Department of Transportation bridge column. We then moved the first specimen into place and began fabrication of our actuator reaction beam and brace. We had to place the column without the loading stub because with the loading stub in place, it would have exceeded the capacity of our 5-ton overhead crane. Also, because we don't have a strong wall, we had to develop a test frame anchored to our strong floor and then lay the columns over on their side to test them. Once the actuator beam was complete, we installed the hydraulic pump and our 100 kip hydraulic ram. The hydraulic ram has a total stroke of 28 inches, so we'll be able to push 14 inches in one direction and 14 inches in the other direction during our cyclic testing. We then designed and installed the loading stub for the first column, including plasma cutting a hole in the inner steel shell so that we could place our 2-inch diameter threaded rod through the column, anchoring it to the loading stub and attaching it to the hydraulic actuator to apply the load. We also extended the PVC ducts through which we were going to place pre-stressing strand to provide our constant axial load during the test, and then installed a fairly light reinforcing cage and then placed the concrete for the loading stub. This is then our first specimen in place with the actuator installed with the load cell and all of the attachments made. We are currently installing our data acquisition system. We will have LVDTs to measure any potential rotation of the column base, so we can remove that from the deflections that we will measure for the column. We'll also measure deflection of the column at mid-height and at the application of the load, as well as the load cell to measure the load from the actuator. The loading sequence consists of cyclic loading, where we start off with a set displacement, pushing it and then pulling it twice, 2 cycles for each increment, and then the subsequent increment is increased by 40%, and we do that until we reach a nice hysteresis loop for the column and then eventual failure of the column. We'll also record the strain gauges from the inner steel tubes and the strain gauges on the reinforcing steel for the reinforced concrete column, and we are installing strain gauges on the FRP tube near the base at the same locations as the strain gauges on the inner steel tube, except these are going to be measuring hoop stresses in the FRP tube, because that hoop stress is what provides confinement to the inner concrete core during testing. That's all I have, and I would be happy to answer any questions you might have.
Thank you very much, Dr. VOLZ. Yes, there's a significant progress since last time. And I like, just a personal comment, I liked very much your test setup, extremely clean. And so when both of us working at CTL, if you remember, we rarely had that cleanness, and so very nice there.
Oh, thank you. I also have to say that we fabricated all of that in-house. The steel we either purchased and had some of it donated, but we did all of the fabrication in-house. So we are. I thank you for saying that, because we're very proud of it.
Great. I know, as an experimental person, I look at my test setup as work of art. That's the thing. So we have a couple of questions, and we have good time to answer them. One question asking, have you considered comparing with an RC column with high strength concrete and high strength reinforcement as a control?
That's an excellent question, and actually, as soon as you said that, I was like, we have to do that no matter what, because that is an excellent comparison. To use a high strength concrete, you know, we were doing this to compare it to what is traditionally used today, but using high strength concrete and potentially 75 KSI yield strength steel, I think would be, and that's an excellent suggestion. I think we need to incorporate that no matter what. I appreciate whoever raised that question. That's a great idea.
Thank you. Next question, when do you anticipate a field implementation?
My hope is that as we finish this up, assuming that we're going to get good results, we can approach the Oklahoma Department of Transportation for potential field studies, perhaps even opening it pursue a pooled fund study because often with applications, the timing is so critical in finding a bridge that is of the right size and right type, and the DOT is of the right nature to let you use it as an implementation project is always difficult. But if we could do perhaps a pooled fund study and enlist a number of states, we might have better success in the timing of finding the right application. I think the results should come out well. I think it will be very close at the conclusion of this project to be at that implementation stage. And we'd love to also involve the ABC UTC as well.
Definitely. And I mean, as you mentioned in the beginning, that was a key statement. You're trying to combine advantages of 3 different systems in one. I believe also you will see the result as it is. The next question asking, it's about your test setup. So does your horizontal test setup limit the range of motion of an actual in-place column?
We don't think that it does. It is cantilevered out from that concrete base. There's about a 5-inch clearance between the actuator supporting beam and the bottom of the loading stub. So we feel that if there is any twisting or displacement perpendicular to the actuator, it will be able to do that. The knuckle on the actuator allows for rotation in alignment with the column as that top head deflects as a long cantilever. So our feeling is it should be fairly free. There's of course always a limit when you're doing full-scale tests. If you allow too much freedom, it can be a little dangerous to the people doing the test. But I think we've got enough freedom for this to represent a good test. It is based on some work that a lot of column testing that was done at Missouri S&T, which was my previous university. It's a very similar kind of test setup, except they had a strong wall they could react out of, so their columns they could at least place vertical. It's a little funny when you lay them over on their sides, but my feeling is we should be able to get good, honest results from the test. But you're right, that is, you're always limited to constraints by the loading apparatus on your specimens and whether it truly represents an actual column in place, which is why an implementation project would be so wonderful, to install instrumentation and see how it behaves over time and see how well it maps to the testing.
That's great. Yeah, no, definitely. Another question, I think we have 2 minutes, 1.5 minutes. Is there a possibility of precasting the column sections to reduce construction time even further?
Yes, that is an excellent question. That is one thing we're going to look at. Dr. Floyd, my co-PI, is focusing on the connections between the columns and the foundation. And one of the options is going to be a splice connection where the column can come out. It can be precast, prefabricated, whether at a precasting plant or even just on site, but away from the actual construction of the bridge. And then you could lower it into place, splice it to the foundation, and be ready to form your pier cap and pour that. So that is one of the connections that we're going to be investigating. That part of the project is part of our companion Oklahoma Department of Transportation project that goes together with this ABC UTC study.
Okay. Thank you very much, Jeff. I really enjoyed your presentation. This is the real thing, really. And thank you very much.